What about D, 1D? So here the question is, you have this set V. And each Vi belongs to Rn. And the condition is k is less than n. And the question is the span of V equal to Rn? Is that right? Yes. Most of you got it right. What is it? Is it correct? Is the span of V equal to Rn when k is less than n? Yes. How many vectors do you need to span Rn? See if, okay, you're talking about R2, and I have only one vector. This is V. This is my V1. I only have one vector. K is less than n. Does this vector span R2? It does. Okay. Well, it does not. Again, it does not span R1. R1 is just sort of single number. It spans a one-dimensional subspace. A one-dimensional subspace has the same dimension as R1. That's all. But it does not span R1. Okay. So here this is false. Because even if the set V is linearly independent, there aren't enough vectors in your set V to span all of Rn. If the set of if the set V is linearly independent, then what can you say about the dimension of the span of V? If this set is linearly independent, there are k vectors, then what can we say about the dimension of the span of V? Okay, you've all forgotten. Okay, it's k. It's a k-dimensional subspace. Just like here, there is one vector. As long as this is not 0, 0, the span of this is some subspace, and the dimension of the subspace will be 1. Okay, so the first one is true. First one is false. Sorry. What about the second one? When k is greater than or equal to n, then is the span of Rn okay. What about this case? False, is it? Okay, why is it false? Okay, sorry. The first question was does not span Rn, so this is actually true. Sorry. That's fine. Yeah. But the argument is the same. Yeah. Here. This is false. Why? Why is this false? Or when can it be false? Can this ever be true? If k is greater than or equal to n? Okay. Okay, all right. Let's say we're talking about R2. Let's say I have two vectors like this. This is my V. Does this span R2? It does not. So when will it span R2? If k is greater than or equal to n? Yes, if V is a linear V, or let me put it this way. If k is greater than or equal to n, if there are n vectors in your set V that form a linearly independent set, then the span of V will be Rn. If, let's say, n is 2, k is, let's say, 100. But if you cannot find two vectors that form a linearly independent set from the set of 100 vectors, then it will never, then the span of the set of these 100 vectors will never span R2. Okay, so the condition really is there need to be, for this to be equal, there need to be in your set V, you should be able to select n vectors that form a linearly independent set. If that is possible, then it's equal. Otherwise, it's won't be equal. Okay. Okay. Then F. Well, in F, you're asked to find out the dimension of span of how you'd find. So we need to find out the dimension of span V. The question is, how would you find out? Assuming that you had that set. Okay, good. What do we do? So we have the set of vectors. Okay, what do we do with them? We test for linear independence with it. Is that what you're saying? Because you're asked to explain. So you have this set. You have to find out the dimension of the span of V. The question is, how would you find out? Basis for what? Which vector space? Rn. Okay. Basis for the span of V. Is it? Okay. If you have the basis for span of V, then how would you find the dimension? Okay. Let's say B is a basis for span of V. Then what? Let's say by some means you got this B. Then what? But your final goal is to find the dimension. Right. Great. Okay. Then the number of elements in this set. Hash simply means you count the number of elements in B. That will be equal to this. That's fine. But how do you get B? All you have are these. How would you find out? All you have is this set. The question is, how would you find a basis B for the span of V? No. See, all we know is the number of elements is k. It could be less than n, it could be equal to n or greater than n. Here. If I had this, how do we find out? Well, here when you see the numbers, you know that it's not a linearly independent set. But if you had any arbitrary set of vectors, how would you find it? Sure, okay. See, the condition is just a definition of linear independence. It does not tell you how to find those. Okay, you're right. So if you're saying apply this condition, and if this is equal to 0, sorry, if this is equal to 0, only when all the alpha is at 0, then this set is linearly independent. But this approach alone does not tell you how. Okay, even if it was linearly dependent, right? Okay, if you had a linearly dependent set, this does not tell you how to find a set of vectors from this that do form a linearly independent set. This is simply the test or the definition of linear independence. Okay, what if you did this? What if I give you a clue. You form a matrix like this. The size of this matrix will be n cross k. If you had this matrix, is it possible for us to find out? See, I call this matrix A. Okay. What if you solve for this? Can that be used to find out how many linearly independent columns you have here? What if you do this? What if you try the QR decomposition? Well, it might fail, but if you continue, can that be used to find out the number of linearly independent columns? These are two possibilities. I won't. I mean, you can think about how you could use these two procedures for find out if a set here or how many what is the dimension of the span of this set, and you will find that that's related to really the rank of the matrix A, where V1 to Vk form the columns of the matrix. You can think about why that is, and then think about if you can use a QR decomposition to get at the rank of A. Okay. Then second one, we have a set of elements equal to 1 that X belongs to Rn. The question was whether this is a linear, if this forms a subspace of Rn, R3. Okay, most of you got it right. This is not a subspace. An immediate check is the zero vector is not in the set. If you substitute 0 here, you'll get 0 equals 1. That means 0 is not, 0 is not in the set of all elements whose second norm is 1. These are essentially points on the sphere. Subspaces are flat spaces. This is curve. The third one, most of you got this right. The unconstrained optimization problem. The question was, does this have a minimum? If it has a minimizer, you're supposed to find the minimizer and then find the lowest value for this function f. Does this have a minimum? What is the condition for it's unconstrained, so we don't have to worry about feasible direction and Lagrange multipliers and all that. We simply have to test one or two conditions. Right? What is the first thing you test? Yes, what is the gradient of this? And this is independent of x. That means it never goes to 0. This is already not equal to 0. So this does not have a minimum. What is the lowest possible value for this function? Is there a lowest possible value? There isn't. If you include infinity in your ream of things, then the lowest possible value is minus n. Okay. So the unconstrained problem does not have a minimum. Then we have this equality constraint. This is really equal to x1 square. How do we solve this now? Yeah, you do the Lagrange multiplier, so you find this we know. And then what is this? Okay, and then what is the condition? At least the first order condition. What is the first order condition for this? For a minimizer. If x star is a minimizer, what is the condition that needs to be satisfied? The Lagrange condition. Equals 0. And of course, 0. What do you get when you do that? What are the three equations you will get? So you have 2, 1, means we have 2 plus 2 lambda x1 equals 0, 1 plus 2 lambda x2 equals 0, and you have this. What do we do from here? Well, there are 3 unknowns and 3 equations. What are the 3 unknowns here? Yeah. So these are your unknowns. Now we can express x1 and x2 in terms of lambda, substitute here, and then solve for lambda. What do you get for lambda? So what is x1? Minus 1 by lambda. X2 will be, yeah. Is that okay? And then if you substitute both of these here, you get some of you might have gotten the numerical values wrong, but I'm not bothered about it. I've given, if I've not given you marks, if you've got this step right, and if you just got the numeric value wrong, it's fine. Just let me know in case I've not given you marks. Okay. So now we have x1. Now what are the possible solutions to these 3 equations now? How many possible solutions do we have? Is there only one possible solution? Okay, before that, what is the geometric picture associated with this? In fact, that's the first thing you should have thought about when you saw the problem. Okay, it's all in R2, so easy to visualize. Where is h of x? H of x is simply this circle. What about your f of x? Sorry? Yes. Where though? How? In what direction? Like this? Like this? No, you cannot shake your head for both options. You have to tell me one option. Like this? Okay, all right. So it'll be uh, if it's 0, so if it's 0, 1, it will come 0, x2 will be, so it will be like this. What direction is the gradient pointing? At any of these lines, what direction is the gradient pointing? My question is, if you move in this direction, is the value of the function increasing or is it decreasing? This is your gradient. Where would the minimum be? Or where would the extremum be for this? If you move, say, the only parts of R2 that you're allowed to search is this circle. You cannot move out of this circle, right? And we know that the extremum occurs when your h of x just touches one of the contours, and similarly here. If that is the case, how many solutions should you have when you solve for that? 2, right? Because this is just a first order condition, which corresponds to h of x just touching one of the contours. So there should really be 2. And do we have 2 solutions here? We do. Lambda is plus or minus 5 by root 2, root 2 by 5, sorry, root 5 by 2. So if you take this to be x1 will be minus 2 by root 5. And if this is equal to minus 5 by 2, then you have those are these 2 points. Now, how do we know which one is the minimum? What does your hunch tell you? Which of these two would be the minimum point? This one, because the gradient's pointing this way. That means if you move in this direction, you're supposed the function will decrease. That means this has to be the minimum. But how do we show that? One simple way to do this is simply substitute both these values in your f of x and find out which is lower. Let's say we call it x star 1 or z. What is f of x star 1? Well, you simply substitute for x1 and x2. First one will be minus 4 by root 5 minus 1 by root 5. The other one will be, this is obviously lower. If of x1 star is lower than this, that means this is the minimum, that's the maximum, and this is the lowest value for the function. Yeah. How do we do the next one? The next one, I can't remember. Yeah, okay. F of x was the same. But your g of x was, what is the geometric picture now associated with this? I remove this. I'm going to just, where is g of x now? It will be a square. Why will it be a square? What is the definition of this? How do we solve this now? Can you apply the KKT condition here? Why not? You said no. Why not? Was it 1 or less than 1? It was equal to 1. So this is still h. Sorry, not a KKT. Means it's equality constraint. So it's still the Lagrange multiplier. Can you do that here? Why not? Yeah, you're right. We cannot apply it here. Why? Yes, exactly. The function is not differentiable here. So there is no gradient that can be defined at this point. So if that cannot be done, how else can we solve this? I just realized I'd done a mistake. I wanted it to be less than or equal to 1. I realize now that this is equal to 1. That's okay. If it is less than or less than 1, that means this one. I'll have to give you marks for this. I will. It's fine. If it's less than, if it's like this, well, the same problem. The gradient does not exist here. And how do you take the derivative of something like this? This is not continuous, especially at the corner points. It'll switch. The gradient will point in this direction, and then the moment you cross this, it'll start pointing here. So that's not the grade. The gradient is still not defined. Let's change this. Can you use the, well, if you were to go about this by applying your intuition, where do you think the minimum occurs here in this case? here, right? Okay. How do you find out if this point is in fact the minimum? What are the feasible directions at this point? Is that okay? Well, both of them cannot be zero at the same time, but both of them have to be positive because that's the only direction you can move. Okay. And what is the condition there? If you know the feasible directions, what is the condition along with the set of feasible directions to find out that that point is in fact a minimum? Greater than or equal to zero. Because if you move, that means if you move in the feasible direction, your function is going to increase because there is a component of the gradient along that direction. Right. Okay. That we can apply it to the boundary points. What about inside? So, for example, at each of these points, you can apply this condition to find out which one of these satisfies this. Right? You can also apply to these boundary lines because you know the feasible directions. What about something inside? Well, inside all directions are feasible. Then you simply have to apply this. Is it clear? At the boundary points, you find the feasible directions and then this condition applies. If you're inside, then this condition applies. In fact, inside none of them go to, it's never equal to zero. So there is no minimum inside or there is no extremum inside. And then if you check these 4 points and check these 4 edges, you will find the only one that satisfies this condition will be this. Okay. All right. Now, if it was a problem like this, how would you solve it now? This was not an inequality constraint like I had done in the question paper. It was an equality constraint. Then how would you test it? Exactly. So there is nothing to test inside. All you have to do is just test along these points because they are not differentiable at these points. You simply apply the feasible directions approach. But here, what are the feasible directions here? How many feasible directions do we have? We only have 2. You can either move in this direction or in this direction. That's it. And similarly here. So here you only have to test for 1, 0 and 0, 1. That's it. Okay. Okay. Then the 4th. Is this clear? The optimization problems? How to go, I mean, at least how to go about solving them? This was about the SVD and the 2 norm. So if A is a 5x4 matrix with a singular value decomposition like this and rank 4. Okay. The question was, what is the second induced norm of A? It'll be sigma 1. And then the question was, okay, you had to, I mean, we derive a matrix B based on A. And then the question was, what was the singular value? Well, if B was equal to A transpose, then what is Why is it sigma 1? Yes. Well, all that will happen is this. Right? The singular values of B are still sigma 1 to sigma 4, and the largest value is sigma 1. So this is sigma 1. If you do a single rank approximation, then what? This will again be sigma 1. What is the SVD of this? Of this B? Well, it's just this. This is U1. That's it. This is SVD. There is only one singular value, which is non-zero. Well, it doesn't matter. If it's zero, then it should be zero. But there is only one singular value. What if you do a third rank approximation? It will still be sigma 1 because that's the largest singular value. Five. Four. Okay. The largest value here is sigma 3. Okay. Okay. There again is a mistake in 4E. Nobody noticed it. I said B equals A inverse. Am I allowed to do that? Does A inverse exist? Hold on. Yes, full rank and what? And what are the conditions? Yes, is A square. So yeah, again, so your marks will be out of 34, not 35. Okay, that was my mistake. Okay. Okay. And then the last one. You're asked to find out the output xn at n equals 5. So you're asked to find out x5, given that x0 is 1, 1, and un is 1, 0 for all n greater than. Most of you got this right. Just a recursive equation that you do. But most of you did not get the next one. Is the system stable? Well, we talked about two types of stability. Well, I really only talked about one. I said we will not talk about Bibo. But some of you have used this to say it's, I think some of you said not stable. I think I've given you marks for that. If I have not, you come and see me. How do you find if we talked about Bibo, but we talked about another type of stability, right? What was that? Sorry? Sorry? No, no. What type of stability did we talk about when we talked about linear dynamical systems? Did I not talk about this? And what determines internal stability? No? So if you have a continuous time system, then if the real part of your eigenvalues are less than zero, then for sure it's stable. If it's equal to zero, it might still be stable. And then if it's for a discrete time system, okay, I think you guys did not revise this lecture. Okay, the absolute value of If it's less than 1, for sure, it's stable. If it's less than or equal to 1, then it depends. Yeah, so the final exam will include like these modules as well. The one on signal processing, the one on linear dynamical systems, the applications of least squares, and also the one that we will see for this module on linear programming. Are there any other questions from the midterm? Okay, if there isn't, then we will move on to the last module. On this is a popular uh, category of optimization problems that comes across in various fields. And because we've done a good amount of linear algebra, I thought, and optimization, I thought this would be a good way to finish the course. Okay. We will primarily do look at the problem and then geometry of the problem and how to go about solving this problem. We will look at applications after we've gone through that. Okay, so we won't do any applications now. We will do applications at the very end. Maybe not tomorrow. I'm not here on Friday, next Monday and Tuesday. So we will have our next class tomorrow, and the one after that will be on Friday. So we'll probably look at applications next Friday. So, so we, yeah, yes, 19th. Is it Friday? No, let's do it Thursday then. Okay, I don't want to delay it too much because if we do it on Thursday, then by the we can have the final exam by the end of this month or early next month. Okay, all right. Okay. I mean, we've seen we've seen problems like this, right? Okay. Linear programming is essentially a set of problems where f, h, and g have a specific form. Okay. Our f of x is a linear function. Okay. Experience. Are you? C, I mean, if I've written this down, C also belongs to R. And there is a set of linearity constraints that A, M cross N, and M. Okay. And in addition to this, there is also this additional constraint where you want all your variables x1 to xn to be all non-negative. And this is, I mean, there are several ways to formulate this. This is called the standard form. Standard, sometimes people might call it standard equality form. And we will only work with this. Okay. And it turns out, I mean, the variations are somebody might say maximize C transpose X. Somebody might, so the other variations could be maximize C transpose X, but the same two conditions apply here. Or people might say minimize C transpose X, but they might say X less than or equal to B, and might say something like this, or greater than or equal to. Again, this could be the equalities could be different as well. So there are all these different forms, and all of them are called linear programs, but each one of them can eventually be converted to something like this. Okay, and we will primarily focus on this because one of the oldest methods for solving this problem is called the simplex method. Okay, that relies on the problem being formulated in the standard form. Okay, so we will always convert any problem that we have in the standard form. Okay. Let's look at a specific example and ask, okay, what is the geometry of this? Because we've always, whenever we've had a problem like this, first thing we did was to see if we can visualize it. Let's say we're talking about R2. Let's say our problem is minimize. So, subject to, right? Okay. What is CAB here? CAB, yes, yeah. What is C? 1, 2. Yes. What is A? Is B. That's fine. That's all. Okay, that's the problem. What is the geometry now associated with this? It's an R2, so it's easy to visualize. So we're really talking about what are the contours of your f of x or C transpose x. Well, at 1, 0, the value is 1. At the value of C transpose x is 1 at 0 half, right? So it's really, it's like this. Let me do one thing. Just change this slightly. Anyways, the contour does not change. I've simply changed the direction in which the function increases. The contours are like this. If we did not have the constraints, is this problem solvable? It's not. Yeah, that was the problem in your midterm. But what do these constraints tell me now? Where is the region I can over which I can search? Well, there are really three of them, right? There are three constraints. No, this is one of the constraints, but now you also have these constraints. So it's not really a straight line. Yes, these two tell me that I can search over this region. Okay? These are all possible set of points, but there is also this additional constraint that needs to be satisfied. And where is that? Sorry, is it like this? Okay, where are the intercepts? You're right, it's like this. Yes, the intercepts, it will intercept at 0, 5, and I'm not drawing it properly, but yes. Right. So, but effectively, so this line is this entire line that passes through your R2. And these two constraints, in addition to that line, tells you that we can only search along this segment, this line segment, nowhere else. Okay. So that's essentially the problem. You are allowed to move along this line between these 2 points, and you find the minimum value for this. Okay, so that's what the geometry of this standard problem looks like. Let's say we had a slightly different version. But instead of equality, we had 5. Now, what is the difference? Well, my contours are the same. I'm still, these two constraints tell me that I'm restricted to this quadrant. What does this tell me? Sorry. Okay, all right. So you still have this line. Where can I search now? Yes. Now the difference between this problem and that problem is there. Here you could only search along this line. Here you can actually search anywhere in this region. So you could search here. That's your feasible region. Here your feasible set was just this line segment. Here your feasible region is this. Okay. I'll leave it there. Leave it at that. Now, because we said we will only work with the standard form, and I said that you can convert non-standard forms like this to the standard form. So whenever you have a non-standard form like this, where there is no equality constraints, all of them are inequality constraints, what you do is you add what are called slack variables. Essentially, you introduce dummy variables in your problem to convert a non-standard version to a standard version. Okay? We don't touch f of x, we leave C transpose x as it is. We take x1, so equals 5, and we have x1 greater than or equal to 0. Okay. So this term has to be always less than or equal to 0. Sorry, less than or equal to 5. Right? So now, if I change this slightly and I say x1 plus x2 plus x3, this is a dummy variable that I'm introducing, and I say this is equal to 5. Okay? This x3 has to be a positive quantity or a non-negative quantity, right? Because this is always less than or equal to 5. That means this value has to be greater than or equal to 0 to take up whatever value, whatever, basically this will be x3 will be equal to 5 minus x1 minus x2. Okay? And because x1 plus x2 is always less than or equal to 5, x3 will always be non-negative, right? So you can do this and then say, well, then this is from the original problem. And then you impose the constraint saying x3, this dummy variable that you introduce, has to be greater than or equal to 0. Is that clear? Okay. I mean, it's straightforward. Maybe initially it's a bit confusing, but once you think about this for a few seconds, then it's clear. Okay. And so essentially, what we've done is we've taken the two variable problem with only inequality constraints, and we've converted that into a 3-variable problem with equality constraint and this non-negative constraint. Okay. So essentially, what's happened is minimize C transpose x less than or equal to b, x greater than or equal to 0, has been converted to minimize C tilde. Okay. I'll get to what this is. And but now your x till where x here was only x1, x2. Okay. Well, this should also be. Okay. X tilde now it's got 3 variables, right? So this will be x1, x2, x3, right? What will be a tilde? What will be a tilde and b tilde? Yes, yeah. A11, is it? Here, your original A was, what will this be? Yeah, it will be 3 ones, and B, this will remain the same. What about C tilde? Because there are 3 variables now. There are only 2 variables here. Yes, so it will be -1, -2, 0. Because our third variable does not appear, I mean, we introduced that slack variable. It was not there in the original cost function. See, now the question is, okay, we've gone from a problem like this, a 2 variable problem, to a 3 variable problem. That means now our search is really in R3, okay, whereas here it was entirely in R2. What is the geometry of this in R3? Shall I take this up? So this problem, we changed it to R. I mean, we've expanded it to R3 so that we can have the problem in the standard form. Now we are really working in R3, and instead of x1, so here this is x1, x2. Here we are working in x1 tilde. Well, x1, x2, x3 really. What is the geometry of this problem? Well, what does this constraint tell me? Well, there are 8 octants, and if these are the positive directions for x1, x2, x3, we can only this constraint tells me that we are constrained to this octant. Okay, what about this? We know that. What will it look like here? Yeah, triangle. Yes, okay. Where does it intersect the 3 axes? 1, 0, 0, is it? Here, a tilde x should be equal to b tilde, which is 5. It won't be 1. All these 3 points will satisfy. Okay, it'll essentially be this. Well, this is the point. Okay, and where are you searching now? There you are searching within the triangle. Where are you searching here? You're only searching on this triangle because both of these have to be satisfied, right? Even though this tells you you're searching in this octant, the intersection of the octant with this is essentially just this triangle. So your search is only here. Okay. So here you're searching over a 2-dimensional region. Here also you're essentially doing the same, even though the problem is posed in 3 dimensions, because you're only searching over the surface of this triangle, on the surface of this triangle. Okay. Okay. Now the question is, okay, fine. We've changed that to this form so that it looks like the standard form. Now the question is, if you let's say there was a way for us to solve this problem. The question is, if I solve this, I'll get some solution. It won't be equal to the solution. It might not be exactly equal to that solution. It might be some solution to this. Now the question is, can you derive that solution from here? Okay. It turns out you can. The only difference is, if you search here, let's say you find a solution somewhere. Okay. In a linear program, the solution is always on one of the vertices. Okay, that's the nature of linear programs. So it'll be one of these vertices, right? And this region here that we had for the problem in R2, that region is still in this picture. That's essentially this region. This is exactly this. All we've done is add a third dimension, and we've essentially pulled this triangle up. That's what we've done by introducing a dummy variable. Okay, so if for simplicity's sake, okay, let's say we're not dealing with a linear program, we're f of x was some non-linear function. Let's say the solution was here. Okay, the corresponding solution for the problem would simply be the projection of this onto the x1, x2 plane. Okay, so all I'm trying to say is you can solve this and then get the solution for that problem. So you don't get into any trouble by switching between the two. The solutions of both of them have a one-to-one correspondence. Okay, so we are okay doing this. Maybe we'll do one example for you guys to get your head around this, and then we'll move on to this. Maximize. Uh, this is all we have. How do we get this into the standard form? This is not in the standard form. What do we do? How many inequality constraints do we have? We have 4. Okay. This is one. Another one. Now, how do we? What do we do here? How do we introduce the slack variables? Well, first we need two things, right? We want Ax equals b, and we want this. Okay. All right. We have one of them in that form already. So x1, this is okay. We don't have to touch this. This is x1 is less than. What can we do here? Well, we could. And then we remove that so that I have space to write. If we add a dummy variable, well, we have x1, x2, let's say x3. This is non-negative. This is less than 1. Whatever is remaining, if x3 has to be positive, and that'll if the size of x3 is such that it's equal to 1 minus x1, then you're fine, right? So we have x1 greater than or equal to 0, and here we also have. So that's fine. What about this? x2. Well, it'd be ideal if we can get it in this form, less than or equal to. Okay. x2. So let's do this. Okay. Now if we do x2, x4 minus 1. Greater than 0. And for this, we have x2, 3. Zero. Yeah. Okay. So effectively now, what's happened if you had a 2-variable problem, because you had 4 inequalities, you've now ended up with what is the size of the problem now? x3, x4, x5. Yeah. So now we have x1, for x2. Now we have x1 plus x3 equals 1. X2 plus x4 equals minus 1. X2 plus 3. Is that right? Yes. And then okay. Your A, so this is your B. What is your A or A tilde? 1, 0, 1, 0, 0. 0 minus 1. See, often what will happen is whenever you have B and you introduce dummy variables, your A tilde will typically have a shape like this. You'll have your original A, and then you'll simply have I, well, not exactly I. You will simply have your unit vectors here, okay, depending on how many unit vectors you had to introduce. So here we had to introduce 3, so you have a I3. Okay. Now, in the previous case, we had one inequality condition, and the original problem was in R2, so we ended up in R3. Here, the original problem is in R2. There are 4 inequality constraints, and now the problem is essentially in R5. So it's again a shape like this over which we search, okay, but in R5. Okay. But there is one more change here. What do we do there? Well, you simply change the sign. C will of course change. It will be 3, 4, 0, 0, 0, because you are not depending on x3, x4, and x5. All right. Okay. See the problem that we talked about earlier. Okay. We had a contours like this. Okay. This is the region over which you can search. And let's assume this is C. Based on this, where do you think the minimum is for this problem? Is it here? Okay. As I said earlier, for a linear program, most often, almost always, the solutions will occur at the vertices of this shape that you have. I've drawn the region over which we are going to search. I've drawn the contours for our objective function, and I've drawn the direction of C. I'm asking where is the minimum? You're saying 0, 0, is it? Sorry? Here, is it? The direction of the gradient is here. It would in fact be here. So the same argument when we were talking about set constraint problems. So here you will find that the gradient of F or C transpose all feasible directions will all be positive, whereas that won't be the case here. Okay, there will still be directions in which if you move, you can still keep reducing your function. So the solution will come out be here. Now, in fact, if instead of this, if we had a more complicated geometry, let's say I had something more complicated like this. Yeah. And I had This is again the direction of C. Where is the solution or the minimum? Well, in this particular case, since I've drawn the contours like this, is likely to be here. Okay. So the point I'm trying to make is the solution for these problems almost always will be at the vertices, okay, of these polygons that I've drawn. Okay, it need not be like that. Okay, can you think of an example where it might not be on one of the vertices? If yeah, if C was parallel to this, if your C was like this, then you don't have a unique solution. Now you have an infinite number of solutions. But still, but the point to note here is there are still two vertices that are solutions, and any edge that joins those two vertices uh, will be a solution to that problem. So with that geometric intuition, right? So if you're dealing with linear programs, except for cases like this, a vertex is always the solution. Vertex of a polygon. Now the question is, if you have your program in the standard form like this, no, you have a question? Okay. Okay. How did I say this is a solution then? Okay. Here. If you are here, right, you can still move in this direction, and any direction in between, and still satisfy your constraints, right? If you move in this direction, right, and your gradient here is like this, the angle between the two of them is greater than 90, right? That means your inner product will be negative, right? Which basically means that you can still move. There are directions in which you can move such that you're moving in the opposite direction of the gradient. That means you're reducing the function. See, again, the same idea. When we talked about the equality constraint or the inequality constraint, we always said whenever your constraint set touches your f of x contour, just touches your f of x contour at a single point, then that is likely to be one of the extrema. Okay, the same idea here. Now, depending on, so for this C, this is the solution. If I flip the direction of C, right, if I say this is the increasing direction, then the solution would be this. If I rotate it differently, then this might be the solution. Yeah? Right. So the question, so at least geometrically, it seems like the vertex being a solution of your constraint polygon seems like a reasonable idea, even though we've not shown it rigorously. Right? Now the question, let's assume that it's true, and it is. Okay. The question is, how do we find these vertices? All we have with us is this: minimize C transpose x equals b, and x greater than or equals 0. So the question is, how do we? Okay. If the solutions are one of the vertices for a linear program, then one possible way to solve this problem is find out all the vertices, simply substitute. Let's say you have the set of all vertices. You simply substitute the values here, and then you find out which one has the lowest value, and you're done. Okay. That seems like a reasonable idea, but it turns out you cannot do that. Okay. The problem being there are too many vertices. For example, in these simple examples that I've shown, you have what, 3 here, 1, 2, 3, 4, 5, 6 vertices here. But the moment you go to, let's say, well, let's do an example, right? If you have a problem where you're searching, let's say the constraint was like this. we don't have to worry about C transpose X. Let's say the constraints were like this: xi less than or equal to 1 CR. That means if I was talking about stuff in R3, then I'm essentially talking about searching over this cube, searching inside this cube. Okay? If the vertices are my solutions, right? If I'm in R3, I have eight vertices. Okay. If I was in R2, how many vertices do I have? 4. It's just a square. What if I was dealing with the problem with 50 variables, and 50 variables with these constraints corresponds to 100 constraints? How many possible vertices do I have? I have this, which is 10 power 15 vertices. It's just not possible to enumerate them and go through all of them. Okay, so a brute force search is not going to work. So we really need a better way of dealing with this problem, because, yeah, even though the solution occurs at the vertices, we can't simply enumerate these vertices. Okay. So it turns out, right, the vertex. So if you have V, okay. Now, if the solution occurs at the vertex, right, that means the solution occurs at the boundary, not inside. Okay. If I'm on the boundary, that means some of these inequalities are equalities. Okay. Or make it more clear. Let's skip the standard version for now. Let's say we only had this, okay? And this essentially corresponds to some polygon like this. Okay? If it's not clear why this represents this, I'll just take a quick detour. And maybe we're anyway out of time. If you had B, okay, and let's say X was from R2, an expression like this, the set of all points that satisfy this is called a half plane. Okay, and the half plane is simply this. This is A transpose X equals B. Let's say this was A. Okay, this is your half plane. Okay. This entire space is a set of all x's that satisfy this. That's why it's called a half plane. Okay. Now I'll remove this. Well, maybe I'll keep it for now. And then now imagine I had this one, A1. Okay. I had another constraint, A2 transpose X. Okay. Well, that corresponds to this. Maybe this. Okay. This is A2, and it's all of this. Let's say I'll call this H1, half plane 1, half plane 2. Where is H1 intersection H2? Well, it's essentially this point. This region is, and any region that is constructed using intersection of a finite number of half planes is called a polytope. Which is essentially, if you have, let's say, n of these half planes, and you do Hn, then that corresponds to a polytope. Okay. If you have, let's say, m such equations, because anyway, for now, let's okay. M such equations, you can express them in the matrix form like this. Right? So this really represents a polytope. Essentially, the intersection of M half planes, okay, where this is M cross N. Okay. Whenever you have a polytope that is non-empty and bounded, finite in size, then that's a polygon. Okay, so this is a polygon. It's simply a bounded polytope that's non-empty. Okay. So you can come up with a set of half-plane equations for this. So essentially, let's say we're dealing with R2. Let's say this was A1, A2, A3, A4, A5, A6. Okay. I can write a 6 cross 2 matrix and a set of B's, 6 B's, such that I get this region in R2, right? And this can simply be my constraint over which I'm trying to solve my linear program. And if it's a linear program and my constraint, my objective function is C transpose X, then it's going to have contours like this. In this particular, let's say this was C. In this case, the solution is going to be here. Okay, and the key to this problem is that the solution occurs at the boundary where some of the inequality constraints become equality constraints, and that turns out to be the key in solving this problem. Okay, we'll stop here and then we'll continue this tomorrow. Yeah, okay.